In this video, we're solving logarithmic equations. Again, I'd like to introduce the one-to-one property for logs. If log base b of x is equal to log base b of y, then x is equal to y. So basically, if you have one log equal to one log, if the bases are the same, then their arguments have to be the same as well. Just like with exponential functions, trying to apply the one-to-one property is always my plan A. And the nice thing about logarithmic equations is you know whether or not you can use the one-to-one property right away. If all terms in the equation contain a log, then you know you'll be able to use the one-to-one property. But it's possible that it's just not ready. You may have to combine multiple logs on one side so that you have a single log equal to a single log, and then you'll apply that one-to-one property. Now, if every term does not contain a log, then that brings us to our plan B, which is to write it in the other form. So, if all terms don't have a log, you want to get your equation so that you're one log equal to a constant, and then you'll rewrite your logarithmic equation in exponential form and solve the resulting equation. Please note that you must do a quick check of your solutions in the original equation. Remember that arguments of logs have to be positive. So once you get your solution, quick check it in the original arguments to make sure that you only have positive numbers. Let's solve natural log of 3x minus 10 equals natural log of x plus natural log of x minus 4. Right away, I notice that every term has a log. That tells me that I'll be able to apply the one-to-one property. To have the one-to-one property work, I need one log equal to one log. I currently have one log equal to two logs, so we are going to combine the two logs on the right using our property of logs. Those two logs are being added together, so to combine them, I'm going to multiply their arguments. Distributing over there in the brackets, our right side becomes the natural log of x squared minus 4x. Now that we have one log equal to one log, we can apply our one-to-one property and set our arguments equal to each other. 3x minus 10 equals x squared minus 4x. And we have a quadratic equation to solve. So I'm going to put all my terms on the right. 0 equals x squared minus 7x plus 10. This factors nicely. X minus 5 times x minus 2, giving us solutions x equals 5 and x equals 2. But remember, we got to do a quick check with our solutions in our original argument. We need to plug it in these three spots and make sure that when we clean it up that we get a positive number. So plugging 5 in, I'm going to get 15 minus 10 is 5. That's positive. Plugging in for x, it's positive. 5 minus 4, also positive. So 5's good for sure. Now we plug in 2 into that first argument. 3x minus 10, that's going to give us 6 minus 10, which is negative 4, so this one's going to have to be thrown out. We have a single solution of x equals 5. Let's try another one. Let's solve log of y minus 3 log of 5 equals 3. So remember, when we don't see a log base there, it's log base 10. Well, every term does not have a log in it, so that tells me right away I won't be able to use the one-to-one property. Instead, I'll have to convert this to exponential form. But in order to convert it to exponential form, I need to have a single log equal to a constant. That means that we're going to have to combine the logs on the left side. Now that minus, right away I'm thinking divide the arguments. However, we have this coefficient of 3 that needs to be dealt with first. A coefficient can be put back as an exponent, making our equation log of y minus log of 5 to the third equal to 3. So I think I'm going to make that 125. Now that we don't have any coefficients, we can combine those logs that are being subtracted by dividing the arguments. That gives us log of y divided by 125 equals 3. Now that we have a single log equal to a constant, we can rewrite it in exponential form. Remembering that this is log base 10, our exponential rewrite is 10 to the third equals y over 125, and we'll solve for y. 10 to the third is 1,000, and then we'll multiply both sides by 125. We get y to be equal to 125,000. Now remember, we always have to quick check our answers to make sure that we get positive arguments in our original equation. And if we plug 125,000 in for y, we definitely get positive arguments. All right, one more example. You know, the last one always has to be a real good one. So here we want to solve log base 3 of log base 3 of x equal to 0. This is the first time that we've seen like a function composition with two logs. But we're just going to apply our properties. I mean, I know right away I can't do one-to-one property because every term doesn't have a log. So I'm going to have to rewrite it as an exponential. In order to rewrite it as an exponential, we need a single log equal to a constant. I mean, we have that. If you look at the outside function, you know, we have log base 3 of something equal to 0. That means that we can rewrite it in exponential form. Our exponential rewrite is going to be 3 to the 0 equals log base 3 of x. 3 to the 0 is 1. And we solve the resulting equation, but the resulting equation is once again a logarithmic equation. So we're going to go through that same process. I have a single log equal to a constant. That means it's ready to rewrite in exponential form. Our exponential rewrite will be 3 to the first equals x. And that gives us that x is equal to 3. As long as our solution checks out in our original equation, we're done. Plugging 3 into our original equation in the argument, we definitely get a positive answer. We get a solution of x equals 3. So although this equation looked pretty scary from the beginning, it was probably the simplest of all the ones that we did. Step back, think, see the bigger picture, and apply the properties.